Hi everyone, it's Johnny again. The Sleepy Physicist has just turned 1 year old. Now I've been part of this community for a while now, and I can honestly say it has meant a lot more to me than I expected. Charlie put so much work into this. The topics, the way everything's explained, really all of it. So if you're into physics and space, then this channel may just become your favorite thing to fall asleep to.
So guys, as Johnny told you, the Sleepy Physicist is 1 year old now. I still can't quite believe that, honestly. Thank you, genuinely. We're sitting just under 25,000 subscribers, and I don't think I've properly said how much that means to me. A friend of mine asked me recently, Charlie, why don't you appear in your own videos? Why don't you show your face, talk to your people? And I told him, half joking, that maybe I'm just too shy for that. But the real answer is that I'd rather put everything into making these videos better for you. And I really love when you notice that. I'll be honest with you. There was a point not long ago where I thought the Sleepy Physicist might not make it, where I genuinely wasn't sure if this would still exist in a few months. And the people who showed up on Patreon during that time, they gave me something I didn't expect. Not just support, hope that this place could survive. We're not at a place yet where I can say with confidence that it'll exist forever. But we're moving. 200 members on Patreon is the number that would put us somewhere stable. Somewhere I can breathe a little. So if this place has ever done something for you, helped you wind down, given you something to hold on to on a quiet night, you can support us there. And if you can't right now, that's genuinely okay. Your presence here is already something. It already counts. Thank you. Okay, let's get into it. There is something sitting in the room with you right now. You probably can't feel it. It has no temperature, not really, not in any way your skin would register. It passes through the window glass, through the ceiling, through you, and it does not slow down. It has been travelling for 8 minutes. Before that, it spent somewhere between 10,000 and 170,000 years moving through something so dense it could barely move at all, and it weighs nothing, or, that's what we're told, zero mass. That's the number physicists assign to it. A photon, a particle of light, has no rest mass. None. You could line up 1 trillion of them and the scale wouldn't budge. The sun is losing 4 million tons of itself every second through these. That's the thing that stops me when I actually sit with it. Not the number. Numbers at that scale stop meaning much after a while. It's the contradiction. The sun is hemorrhaging mass, shedding substance, physically becoming less of itself with every second that passes. And the mechanism is something that by formal definition has no mass to speak of. Something that doesn't exist when it isn't moving. Something you cannot hold, cannot weigh, cannot slow down without destroying it entirely. I've turned this over a lot and I'm still not sure I've landed on the right way to think about it. Here's what I mean. When we say something weighs nothing, we usually mean it doesn't matter. A breath of air, a whisper, something negligible, something you wave away. But the light leaving the sun right now is not negligible. It is the reason this planet is warm. It is the reason anything on it grew. It bends around massive objects. It slows down ever so slightly though when it climbs against gravity. It pushes things. Spacecraft have been built to use it as a sail, a thing that weighs nothing. Pushing spacecraft. There's a word for this kind of situation in physics. Not paradox exactly, physicists are careful with that word. But there is a real tension here, something that resists easy language. We have a quantity called mass and a quantity called energy, and for most of human history those were two completely separate ledgers. You had matter on one side, you had energy on the other. A rock had mass, a fire had energy. Different categories, different rules. The sun is losing mass through energy. Those two sentences, and I mean this plainly, should not be able to exist in the same universe under the old rules. Energy doesn't have mass. Mass doesn't become energy. They're different things. Except the sun is lighter today than it was yesterday. By about 350 billion kilograms, give or take. All of it radiated away as light. Something that formally has no mass. So either the sun is wrong or the categories are. I don't want to resolve that yet. I want to stay here for a moment, in the strangeness of it, the specific strangeness of a star slowly spending itself into light and the light arriving here weighing nothing, and somehow still carrying the mass with it. There is a framework that makes all of this coherent. It has been tested more thoroughly than almost any idea in the history of science. It holds up to measurement in ways that still seem improbable. But the framework comes later. For now, the room is quiet. The light has been travelling since long before any of us were born. And the sun is, at this exact moment, 4 million tons lighter than it was 1 second ago. The word that causes the problem is rest, not mass. Mass we think we understand. Mass is the stuff of things, the heft. The reason a stone falls faster in your imagination than a feather, even though that's not quite right either. But never mind. Mass feels like something you could grip. Rest, though. Rest is the word doing the quiet damage here, moia, and I don't think it gets enough attention. When a physicist says rest mass, they mean something very particular. They mean, imagine you could bring this object to a complete stop. Put it in a hypothetical room where nothing is moving. No orbit, no spin, no thermal jitter. Completely perfectly still. Now measure its mass. That number, the mass of a thing at absolute rest, is its rest mass. It's the baseline, the irreducible quantity. For an electron, that number is tiny but real. For a proton, slightly less tiny but real. For you, sitting or lying wherever you are right now, the rest mass is whatever you weigh in a universe that has stopped moving, which is, well, approximately what you weigh anyway, given that you're not moving particularly fast relative to anything that matters. For a photon, the number is 0. And here is where the language starts to buckle. 0 rest mass sounds, on first hearing, like it means nothing is there. Like the photon is a ghost, an accounting error, something that exists on paper but wouldn't register if you somehow held a scale up to it. That's the intuition the phrase triggers. I had it for a while, this vague sense that calling something massless was basically a polite way of saying it barely counts. But the definition contains a hidden flaw in its own logic, a flaw that only shows up when you apply it to light. Rest mass is the mass of something at rest. A photon cannot be at rest. Not in the sense that it moves very fast or that it's hard to slow down, or that slowing it requires enormous energy. No, a photon cannot exist at rest. It is not a thing that moves. It is, in some sense, movement itself. If you could somehow freeze a photon in place, which you cannot, not even in principle, it would cease to be a photon. It wouldn't be a very slow photon, it would just be gone. The concept of rest, applied to light, is like asking what a wave looks like when the water is completely still. The wave doesn't slow down, it stops existing. So when we say a photon has 0 rest mass, we are doing something a little strange. We're applying a measurement to an object that can never satisfy the conditions for that measurement. It's a bit like... No, actually, let me not reach for an analogy here. Because the analogies I've tried all end up being more misleading than the original thing. What matters is this. The rest mass being 0 does not mean the photon has no energy. These are separate quantities, and conflating them is where most of the confusion lives. A photon carries energy. That part is not subtle or contested, it's measurable, practical, and demonstrated every time light knocks an electron loose from a metal surface, which happens in solar panels millions of times a second. The energy of a photon is real. It is proportional to its frequency. A gamma ray carries more energy than a radio wave not because it has more mass, but because it oscillates faster. The energy is entirely in the motion, entirely in the frequency, entirely in the fact that it is moving at the speed of light and cannot do otherwise. And here is the thing that took me a while to sit with properly. Energy and mass are not as separate as they feel. We have been taught to keep them in different drawers. Mass over here, energy over there, each with its own units, its own intuitions, its own rules. But the universe does not appear to respect that filing system. A particle with energy behaves in many of the ways that matter. Like a particle with mass. It responds to gravity. It has momentum. It can exert pressure. The photon has no rest mass, and yet it does all of these things, which means that either energy is a kind of mass, or mass is a kind of energy, or, and this is closer to what the physics actually says, The distinction we drew between them was always a little artificial. A convenience, a way of describing two faces of something that doesn't have a clean English name. Zero rest mass is not the same as zero consequence. It is not the same as weightless, not the same as insubstantial, not the same as irrelevant to the gravitational bookkeeping of the universe. The photon has no rest mass because it cannot rest. What it has instead is something that behaves very much like mass in every situation where mass is supposed to matter. That should feel slightly unsettling. Not alarming, just unsettling in the way that a familiar word starts to look strange after you've stared at it too long. Rest. Mass. We have been using these words as though they described fixed, obvious, unambiguous things. And for most objects, for most purposes, they do. But push them toward the edge, push them towards something that exists only in motion, that was never still, that cannot in principle be stopped, and the words start to show their seams. There's an equation that resolves this. It's longer than E equals mc squared. Most people have never seen it written out. That's the next place this goes. Everyone knows the equation. It is on coffee mugs. It has been tattooed on people. It appears in films at the moment when a character is supposed to seem intelligent, usually written on a chalkboard in the background while someone says something dramatic in the foreground. E equals mc squared. 5 characters, the most recognised string of symbols in the history of science, probably. And it is incomplete, not wrong, that part matters. The equation is not wrong. For a particle sitting still, for an object with mass and no momentum worth mentioning, it holds up perfectly well. It tells you something real and useful and genuinely strange, that the mass of a resting object and its energy are the same quantity, separated only by a very large number. That's not nothing. That's an enormous claim about the nature of reality, and it's correct. But it is a special case, a cropped version, and the cropping removes exactly the part that explains how a photon, a massless particle, can carry energy at all. The full equation reads like this, in plain language. The total energy of a particle squared equals the sum of 2 separate terms. The first term is its momentum multiplied by the speed of light, all of that squared. The second term is its mass multiplied by the speed of light squared, all of that squared again. Energy squared equals momentum times c squared, plus mass times c squared squared. It looks unwieldy written out like that. But what it's actually doing is clean. It's saying a particle's total energy comes from 2 sources, from its mass and from its momentum. These are separate contributions, independent. You can have one without the other. Now apply that to something at rest. A stationary object has no momentum, or close enough to none that we can ignore it. So the momentum term vanishes. What remains is just the mass term. Energy equals mass times the speed of light squared. The famous version. The cropped photograph. Now apply it to a photon. A photon has 0 rest mass, so the mass term vanishes entirely, drops out, gone. What remains is only the momentum term. The photon's energy equals its momentum multiplied by the speed of light. That's it. That's where all the energy lives. Not in mass, in momentum. In the pure unbroken motion of something travelling at sea, which it has always done and will always do, and, as we established in the previous chapter, cannot stop doing without ceasing to exist. I want to stay with this for a moment because I think it's the sentence that actually resolves the confusion from before if you let it land properly. The photon has energy, real, measurable, consequential energy. It can knock electrons off metal. It can warm skin. It can, in sufficient quantity, push a spacecraft. All of that energy lives entirely in its momentum. There is no mass hiding underneath it. No resting substance, just motion, perpetual and total, carrying every joule the photon possesses. And now, here is the part that took me longer than I'd like to admit. Momentum is not massless in its consequences. A thing with momentous, regardless of how that momentum arises, regardless of whether there's a rest mass underneath it, interacts with the world. It pushes, it carries force, it responds to gravity, because gravity in the relativistic picture doesn't just pull on mass, it pulls on energy, on momentum, on the full right-hand side of that equation, not just the second term. This is why the photon bends around massive objects, not because it has hidden mass, because it has energy and momentum, and the geometry of space near a massive object curves in a way that affects anything moving through it, anything at all, massless or otherwise. The famous equation, the cropped one, implies that energy and mass are interchangeable because for a resting particle they are. But the full equation says something quieter and, I think, more honest. It says energy has more than one source. Mass is one of them, momentum is another. And for certain things, for the things that can never stop, mass contributes nothing, and momentum contributes everything. A photon is pure momentum, nothing else underneath it. That is a strange thing to be. It means the photon's energy is entirely relational. It exists because the photon is moving, and it is exactly as large as the motion is. A high-frequency photon oscillating faster has more momentum and therefore more energy. A low-frequency photon moving just as fast but oscillating slowly carries less. Same speed, different energy, the speed of light is fixed. The energy is not. And the difference lives entirely in that first term, the momentum term, the one the coffee mug leaves out. I don't think this is a pedantic distinction. I think this is the distinction. Because once you see that energy has two separate sources, mass on one side, momentum on the other, the question of how something massless can still affect the physical world stops being paradoxical. It just becomes arithmetic. The sun is radiating 4 million tons of itself per second as photons. Each photon carries zero rest mass and a very specific quantity of momentum. And that momentum is real enough to bend around stars, to push metal foil in a vacuum, to subtract measurable mass from the largest object in this solar system. The equation was always complete. We just weren't showing the whole thing. The paper is 3 pages long. That's the first thing that surprises people. 3 pages, published in the journal Annihilation de Physique on the 21st of November, 1905. It followed 3 other papers Einstein had submitted that same year. One on the photoelectric effect, one on Brownian motion, one laying out the special theory of relativity. And by the time this 4th one arrived, the editors must have been developing a particular feeling about this patent clock from Bern. The paper has no title that announces its importance. It asks plainly, as if it were a question someone might ask over a meal, does the inertia of a body depend upon its energy content? That's it. That's the whole setup. And the paper, for its first 2 pages, is almost uncomfortably dense. It works through the mathematics of body emitting light, using the framework Einstein had already established in the relativity paper, and it does this carefully, without flourish, in the way someone works through something they're genuinely not yet certain about. There is no triumphant tone. If you came to it expecting the announcement of the most famous equation in history, you would read all the way to the end and wonder if you'd missed the moment. Because the equation E equals mc squared does not appear. Not once, not in that form. What appears instead is a sentence. In German, in the passive voice, stated as a conclusion that follows from what came before rather than as a discovery being unveiled. Translated into English, it reads something like, if a body gives off energy L in the form of radiation, its mass diminishes by L divided by c squared. That's the claim, not a formula. A sentence about subtraction. A body gives off energy. Its mass goes down by a specific calculable amount. Now let me walk through what Einstein actually did to get there, because the thought experiment is simpler than the mathematics around it, and the simplicity is the point. Imagine a body. He uses that word, body, not particle, not atom, just body, deliberately vague, sitting at rest. It emits 2 pulses of light simultaneously, one in each direction, equal in energy, perfectly opposite. Because the 2 pulses go in opposite directions with equal energy, They carry equal and opposite momentum. They cancel. The body doesn't move. Its velocity before and after emission is identical. So far, this is almost boring. A thing sits still, emits light symmetrically, stays still, nothing dramatic. But Einstein then asks, what does this look like from a different reference frame? From the perspective of an observer who's already moving relative to the body. In that frame, the two light pulses are no longer perfectly symmetrical. One is slightly blue shifted, one is slightly red shifted, because of the relative motion. The energies are no longer exactly equal. And when you work through the mathematics of what the body's energy is before and after emission in both reference frames, and you require the results to be consistent, which they must be because the laws of physics don't change depending on who's watching, something falls out of the algebra. The body's mass has decreased. Not its velocity, not its momentum, its mass. The body sitting still, emitting light, becomes measurably, calculably lighter by exactly the amount of energy it radiated, divided by c squared. Einstein's conclusion at the end of those 3 pages is written in the same plain, almost cautious register as the rest of the paper. He says, and I'm paraphrasing closely here, that the mass of a body is a measure of its energy content, that if the energy changes, the mass changes in the same direction by a proportional amount. He does not say they are equivalent. He says they are, in some sense, the same thing being measured twice. That distinction mattered to him. It still matters. Equivalence implies 2 separate things that can be exchanged, like currencies. What Einstein was pointing at was more stubborn than that. Mass and energy don't trade places. They are not 2 items on opposite sides of a ledger. They are one conserved quantity that appears differently depending on the conditions. A resting body holds that quantity as mass. A moving body holds some of it as kinetic energy. A body that radiates light transfers some of it outward, and its mass, the measure of what remains, drops accordingly. The sun radiates. Its mass drops. Not because energy is leaking out of a container called mass, because the container and the contents are the same material. 3 pages, no fanfare, a question in the title, an answer in a sentence near the end, and a conclusion so compressed it is easy to read past without registering what it has just said. Einstein apparently mentioned, in a letter written not long after, that the thought might be verified experimentally using radium, a substance with high enough energy content that the mass change might be detectable. He was right about that. It took a few decades, but the verification came. It came in ways he probably did not anticipate, in scales he may not have imagined. The 3-page paper asked a quiet question. The answer, it turned out, was written in the cores of every star that has ever burned. In 1865, a Scottish physicist named James Clerk Maxwell submitted a paper to the Philosophical Transactions of the Royal Society. It was long, the kind of long that signals someone working through something in real time rather than presenting a finished thing. And it was dense in the way that Victorian scientific prose tends to be dense, which is to say, not difficult because it is hiding anything, but difficult because it was written by someone who assumed the reader had already read everything else. The paper was called A Dynamical Theory of the Electromagnetic Field. Freeman Dyson, decades later, would call its publication the most important event of the 19th century in the history of the physical sciences. Maxwell in 1865 was 33 years old and almost certainly did not think of it that way. He was working through a problem about electricity and magnetism. He wanted to understand how the two related. What emerged from that work was something larger than the original question, as tends to happen when the mathematics is honest and the person doing it patient enough to follow where it leads. What Maxwell showed, across those dense pages, was that electricity and magnetism were not 2 separate phenomena, but 2 aspects of a single field, the electromagnetic field, and that disturbances in that field propagated outward as waves. He calculated the speed of those waves using only the known properties of electricity and magnetism, numbers measured in laboratories with no reference to light at all, and arrived at a figure so close to the measured speed of light that he concluded, with characteristic understatement, that light itself was probably an electromagnetic wave. That part is well known. The unification of light and electromagnetism is the headline. The quieter result is what matters here. Buried inside the mathematics of Maxwell's equations, not announced, not highlighted, not given its own section, was the implication that electromagnetic waves carry momentum, that a beam of light, propagating through space, possesses something physically equivalent to the momentum of a moving object, and that when that beam strikes a surface, it transfers that momentum. It pushes. Maxwell noted this. He wrote about radiation pressure in his 1873 treatise on electricity and magnetism, working out the magnitude of the force that light should exert on a surface exposed to it. The number was very small, measurably small, he thought, possibly verifiable in a well-designed experiment, though the precision required would be considerable. He was right on both counts. The number was small, and the experiment would take another 3 decades to pull off. But here is the thing that sits with me about 1865. Maxwell's equations contained the answer to a question nobody had yet asked. The question, can light exert physical force? Does it carry momentum? Does it participate in the mechanical accounting of the universe? That question was not yet on the table in any serious way. The idea that light might push things was old, loosely intuited, not yet formulated. And yet the mathematics Maxwell wrote down to describe something else entirely, the relationship between electricity and magnetism, had the answer embedded in it like a fossil in the rock. It was there. It had always been there, in the structure of the equations. Nobody had looked for it yet. This is not an unusual situation in physics exactly. Mathematics routinely knows more than the people using it, or knows it sooner, or knows it in a form that takes years to translate into plain language. But there is something particular about this case, about the gap between 1865 and 1905, 40 years during which the answer to a major question about the nature of light sat inside a set of equations that every serious physicist in the world had access to, was expected to know, spent careers working with. The momentum of light was not hidden. It was, and I keep returning to this word, sleeping, present but unactivated, waiting for someone to ask the right question in the right way. Maxwell himself seems to have understood, at least in outline, what the momentum implied. He understood that light exerts pressure. He calculated it. But the further implication, that this pressure, this momentum meant light participated in the same physical reality as matter, that it could be bent, that it responded to gravity, that it carried something functionally equivalent to mass. That step was not taken in 1865. The mathematics supported it. The conceptual framework to recognize it didn't exist yet. Einstein's 1905 paper supplied that framework. But when Einstein wrote down his conclusions about mass and energy and the relationship between them, he was not working in a vacuum. He was working in a world where Maxwell's equations were already there, already showing what light could do, already containing the strange implication that something apparently weightless could push a physical object hard enough to measure. The answer was sleeping in the mathematics for 40 years. And then someone asked the question, and it woke up. Comets do something that shouldn't bother you until it does. They move through the solar system in long elliptical paths, falling toward the sun and then swinging back out again, and as they travel they grow a tail. That much is familiar. The tail is what makes them visible from Earth, what makes them the kind of object that stopped whole armies in old accounts, that caused chroniclers to write things down. The tail is the point, but the tail does not behave the way a tail should. A tail in the intuitive sense streams behind the thing that carries it. A comet falling toward the sun should trail its tail outward, away from the sun, behind it as it falls. And when it swings around and begins its long retreat back into the outer solar system, the tail should flip, should now stream behind it in the other direction, pointing back toward the sun. It doesn't. The tail always points away from the sun, falling in or pulling away. It doesn't matter. The tail is always pushed outward, always streaming in the direction away from the sun, regardless of which way the comet is travelling. A comet retreating from the sun moves tail first, which is to say the tail is not trailing behind it but leading ahead of it, pointing in the direction of travel, running away from something. Johannes Kepler noticed this in 1619. He was working on other things, the laws of planetary motion that now carry his name. The long stubborn work of fitting ellipses to the orbits Tycho Brahe had spent decades measuring. And the comet tail observation was something he recorded and tried to account for without, as far as we can tell, being entirely satisfied with his own explanation. He proposed that the sun was pushing the tail, that something emanating from the sun was physically shoving the material outward. He didn't have a mechanism, he didn't have a word for it. The concept of radiation pressure didn't exist. Maxwell's equations were 2.5 centuries away, and the idea that light itself could exert physical force was not yet a serious scientific proposition. Kepler just looked at the geometry of it and concluded that whatever the sun was doing, it was doing it outward in all directions, and the comet's tail was being pushed along with it. He was right. That part is worth sitting with. He was right for reasons he had no way of accessing. The tail of a comet, or at least one of its tails, because comets can have more than one, which is its own strange thing, is made of fine dust and gas released as the comet warms near the sun. This material is light. Not light as in luminous, though it is that too, but light as in low mass. Fine particles. And fine particles, it turns out, respond measurably to the pressure of sunlight. The photons streaming outward from the sun carry momentum. When they strike the dust particles in the comet's coma, the hazy envelope around the nucleus, they transfer that momentum. A nudge, each one. Individually nothing. Collectively enough, across the billions of photons hitting billions of particles every second, to physically move material, to push it outward, away from the sun, persistently and without pause, regardless of which direction the comet itself is heading. The comet moves. The tail doesn't follow. The tail is being held in place, or rather continually pushed to the same place by light. Kepler had no access to any of that machinery. What he had was the observation and the willingness to take it seriously enough to propose a cause, even when the cause was, by the standards of his time, a fairly strange thing to suggest. That something coming from the sun was pushing the comet's material outward. That the sun exerted some kind of outward influence, not just gravitational pull, but something else, something that acted on small things differently than on large ones. The solar wind contributes too, as it happens. Charged particles streaming outward from the sun also push comet material, and this produces a second, slightly different tail that points in a slightly different direction, which is why comets sometimes appear to have two tails at once. But the dust tail, the broad, bright one, that one is light. That one is photons doing exactly what Maxwell's equations would eventually show they had to do, and what Kepler watched them do in 1619 without knowing what he was seeing. There's something about that gap, 400 years between the observation and the mechanism, that doesn't resolve neatly. He saw it. He couldn't explain it. And the thing doing it was light, which at that point in history was simply what let you see things, not something that could push them. The problem with measuring radiation pressure is that almost everything else is louder. Heat, for instance. When light strikes a surface, it warms it, and warm surfaces in air create convection currents, tiny movements of gas, which push on things. The push from the gas is orders of magnitude larger than the push from the light itself. So if you build an apparatus, shine light on it, and watch it move, what you're almost certainly measuring is not radiation pressure. You're measuring the air moving because the surface got warm. This is what the Crookes radiometer does. That glass bulb with the little spinning vanes you've probably seen. Dark side, silver side, spinning when light hits it. Most people assume it demonstrates radiation pressure. It doesn't. It demonstrates thermodynamics. The dark side gets warmer, heats the surrounding air unevenly, and the air pushes. The light is almost incidental. Pyotr Lebedev knew this. He was a Russian physicist working in Moscow in the 1890s, and he spent years, not months, designing an experiment that could separate the two effects, the real signal from the thermal noise, the light's actual push from the warm air's louder shove. His solution was to remove the air almost entirely. He built his apparatus inside a chamber evacuated to a very low pressure, low enough that the thermal convection effect shrank to something manageable. Then he designed the targets, small thin discs of metal, one side reflective, one side absorbing, suspended on a fine fibre. The logic was straightforward enough in principle. If radiation pressure is real, a reflective surface should experience more force than an absorbing one, because a reflected photon transfers twice the momentum, once arriving, once departing, while an absorbed photon transfers its momentum only on arrival. The difference between the two would be the measurement. Straightforward in principle, brutally fussy in practice. The fibre suspending the discs had to be thin enough that even the tiny force from light could rotate it detectably, which meant it was also thin enough to be disturbed by almost anything else. Residual air currents, temperature gradients in the glass, vibration from the building, the experimenter moving too quickly nearby. Lebedev apparently had to wait for the building to settle before taking readings. He had to control the temperature of the room. He had to account for the fact that even his near vacuum was not perfect, and that the remaining gas still created some thermal effect that had to be calculated and subtracted. This is the part of experimental physics that rarely gets described. The long, unglamorous business of ruling things out, of sitting with an apparatus that might be working and might be measuring something completely wrong, and slowly, carefully eliminating every alternative explanation until what remains is the thing you were looking for. Lebedev found it. In 1899, after the years of refinement, his apparatus rotated in the direction and by the magnitude that Maxwell's equations predicted. Reflective surfaces pushed more than absorbing ones. The ratio matched. The light was pushing. Newton's third law says that for every action there is an equal and opposite reaction. It makes no exceptions. It doesn't say except for light, or except for things moving at sea, or except when the force is very small. If light exerts force on a surface, the surface exerts equal force on the light. If the light pushes the vein pushes back. This sounds obvious stated plainly, but the implication is not trivial. It means light is a participant in the same mechanical accounting as everything else. It cannot exempt itself. It cannot pass through the physical world without the physical world responding. Lebedev's experiment made light answer for that. What strikes me about it, and I've thought about this more than seems reasonable, is how quiet the demonstration was. The vanes rotated by an amount you would not see with your eyes. The force involved was so small that the entire experimental challenge was simply making it visible above the background noise. This was not a dramatic demonstration. No flash of light, no visible movement, no moment where something obvious happened. Just a fibre rotating by a tiny angle, in a glass bulb, in a room in Moscow in 1899. And yet, a beam of light had pushed something, not warmed it, not ionized it, pushed it, transferred momentum to it in exactly the amount Maxwell said it would, 34 years after Maxwell wrote down equations that implied it had to. Kepler had watched it happen at the scale of a solar system in a comet's tail with no explanation. Now it had happened on a laboratory bench, measured, quantified, repeatable. Light was not just what let you see things, it was something that Newton's laws applied to. Something that could be on one side of an equation about force and momentum and have the equation balance. That is a different kind of object than anyone had been thinking about when they first started studying light. Start with the surface. The surface of the sun, the photosphere, the part that hurts to look at, sits at roughly 5,800 Kelvin. That is hot in any register you might apply to it. Hot enough that nothing we think of as solid exists there. Hot enough that atoms lose their outer electrons and move as plasma. A state of matter that behaves something like gas but is threaded through with electromagnetic fields that gas isn't. The surface is violent, churning, granulated into enormous convective cells, each one roughly the size of Texas, rising and sinking constantly, carrying heat upward from below. And that's the surface, that's the outside. Now go inward. The Sun has a radius of about 700,000 kilometres. The core, the region where fusion actually occurs, occupies roughly the innermost 20 to 25% of that radius. So you are descending maybe 150,000 kilometres into an object that is already not like anything on Earth, and the descent is not linear. The temperature does not climb steadily and then plateau. It climbs and keeps climbing, and each order of magnitude you pass through is a different kind of wrong, by which I mean a different regime, in which matter behaves in ways that have no earthly analogue, and for which the usual intuitions simply stop applying. By the time you reach the core, the temperature is approximately 15 million Kelvin. Let that number sit for a moment before moving past it. The surface was 5,800. The core is 15 million. These are not points on the same scale in any way that feels continuous. The surface would vaporize any material humans have ever made. The core would vaporize the concept of molecular structure. At 15 million Kelvin, there are no atoms in the usual sense. There are nuclei, protons and neutrons bound together, and there are free electrons, and the two populations move through each other at speeds so high that the idea of one particle being associated with another, of electrons belonging to nuclei, has no meaning. Everything is stripped. Everything is moving. The density at the core is approximately 150 grams per cubic centimetre. Water is 1 gram per cubic centimetre. Lead is about 11. The densest naturally occurring element on Earth, osmium, sits at just over 22. The solar core is 150. A cubic centimetre of it, a space roughly the size of the tip of your thumb, would weigh about as much as a large book. Except it wouldn't look like anything. It would look like nothing, because it is plasma, because it has no surface, no colour in any ordinary sense, no texture you could describe by analogy to anything you've touched. And the pressure holding it at that density is the weight of the entire Sun, pressing inward from above. This is the thing that takes a moment to feel properly. The core is not dense because of some intrinsic property of the material there. It is dense because 1.989 times 10 to the power of 30 kilograms of star is sitting on top of it. The inward gravitational pull of that mass compresses the core until the pressure is high enough and the temperature is high enough to resist it. This is the balance the Sun lives in. The core pushing out through fusion energy, the star's own gravity pushing in. Not a stable state in the way a table is stable. A balance between two enormous forces, maintained continuously, adjusted constantly, held in place by the rate at which the core generates energy. If the rate drops, the core contracts, the temperature rises, fusion accelerates. If the rate increases, the core expands slightly, the temperature drops. Fusion slows. The Sun is self-regulating in a way that is almost too tidy to trust. Now, into that environment place 2 protons. A proton carries a positive electric charge. So does every other proton, like charges repel. The closer 2 protons get to each other, the harder they push against each other, and the relationship is inverse square, meaning that as the distance halves, the repulsive force quadruples. The force doesn't grow linearly as they approach. It grows stubbornly, then violently, then at a scale that at close range becomes almost difficult to think about clearly. The strong nuclear force, the force that can bind protons together into a nucleus, is extraordinarily powerful, but it is also extraordinarily short range. It operates only at distances on the order of a femtometer, which is 10 to the power of negative 15 meters, which is roughly the diameter of a proton itself. To get 2 protons within range of the strong force, you have to get them within 1 proton width of each other, which means you have to push them past the full electrostatic fury of 2 positive charges at very close range. At 15 million Kelvin, with the protons moving as fast as that temperature implies, the average proton still doesn't have quite enough kinetic energy to do this. The thermal energy at the core gives proton speeds that are, and here I want to be careful not to overstate it, almost enough. Not quite enough. Almost. Which means fusion should barely happen at all, which means there is something else going on. The temperature, the density, the pressure, All of that builds the stage, but the play itself, the moment when two protons actually bridge that gap, requires something the stage alone cannot provide. Something that classical physics has no room for, and that took the development of quantum mechanics to name. Classical physics is not wrong exactly. It describes the world you move through with very good accuracy. Bridges stay up, balls follow the arcs you'd predict, gases behave as expected when you heat them. For objects at the scale of everyday experience, things you can hold, see, drop or drive, classical mechanics works. It worked well enough to get humans to the moon. It is not a failed framework, it is a framework with a boundary, and the boundary is small. Below a certain scale, something changes. The rules don't break dramatically, they just stop applying. Like a map that is accurate for roads but has never accounted for footpaths. You follow it faithfully, and then you step off the edge of what it knows. The Coulomb barrier is a classical idea. Two protons repel each other electrostatically, and the closer they get, the harder they push apart. And at some distance, the repulsion becomes so strong that a proton with any given kinetic energy simply cannot proceed further. It hits the wall, it bounces. This is the classical picture, and it is internally consistent and at solar core temperatures, 50 million Kelvin, protons moving very fast but not fast enough. The barrier should win. Almost every proton thrown at another proton should be deflected. Fusion should be extraordinarily rare. Rarer actually than it is. The sun is too dim for classical physics. Not too bright. Too dim. If the fusion rate were governed purely by which protons had enough thermal energy to classically surmount the Coulomb barrier, the sun would produce far less energy than it does. This is not a modern reinterpretation. Early 20th century astrophysicists ran the numbers and found a mismatch. A quiet, persistent discrepancy between what classical mechanics predicted and what the sun was visibly doing. Something was supplementing the thermal energy. Something was getting protons across a barrier they should not have been able to cross. Quantum mechanics supplied the answer, though answer might be too tidy a word for it. What quantum mechanics applied was a framework in which the question itself had to be reframed. In classical physics, a particle either has enough energy to cross a barrier, or it doesn't. The barrier is a wall. You clear it or you don't. Position and energy are definite quantities. The particle is somewhere specific, moving at a specific speed, and the calculation of whether it gets through is straightforward. In quantum mechanics, a particle doesn't have a definite position in the same sense. It is described by a wave function, a mathematical object that spreads out across space, assigning probabilities to different locations. The particle is not somewhere specific until it interacts with something that forces it to be. Before that interaction, it is distributed, smeared, in a loose sense, across a region of space. Now put that smeared probability distribution up against a barrier. In the classical picture, if the particle's energy is below the barrier height, the wave function simply stops at the wall. Nothing gets through. In the quantum picture, the wave function doesn't stop. It decays exponentially rapidly as it penetrates into the barrier region, but it doesn't reach zero immediately. If the barrier is thin enough, some of the wave function survives to the other side, and where the wave function has amplitude, the particle has probability of being found. This means a quantum particle has a non-zero probability of appearing on the other side of a barrier it classically cannot cross. Not by going over it, not by going around it, through it. The particle, and this is where the language starts to strain, doesn't travel through the barrier in any path you could trace. It simply has a probability of being on this side and a probability of being on that side, and sometimes when you look, it's on that side. The transition doesn't have a trajectory. There's no moment of crossing. There's a before and an after, and nothing in between that classical language can describe. I want to be careful here. This is not a metaphor or a pop science simplification. This is what the mathematics actually says, and it is experimentally verified in so many contexts. Tunnel diodes, scanning tunneling microscopes, nuclear decay chemistry, that its reality is not in question. It is strange. It remains strange even after you understand it. The strangeness doesn't dissolve with familiarity, it just becomes a strangeness you've learned to work with. In the solar core, at 15 million Kelvin, quantum tunneling supplements the thermal energy of the protons. The protons don't need to classically surmount the Coulomb barrier because they don't need to surmount it at all. A small fraction of them, a very small fraction, because the probability drops steeply with barrier thickness and particle energy, tunnel through it. And small fraction, multiplied by the number of protons in the solar cores, which is a number so large the word astronomical undersells it, equals enough fusion events per second to maintain the sun's luminosity. The sun shines because particles do something forbidden, not occasionally, not in some exotic experimental regime, continuously right now. Every second, in the core of the nearest star, protons are appearing on the other side of a barrier. They do not have the energy to cross, and the energy released in the fusions that follow is what keeps this planet warm. I don't think this becomes less strange with repetition. I've sat with it for a while and it still has a particular quality, not of mystery, not of the unknowable, but of something real and confirmed and routine that nonetheless refuses to feel ordinary. The sun exists because quantum mechanics permits what classical mechanics forbids. That's not poetic language, that's the situation. The tunneling probability for any given proton is very low, vanishingly low, which means a single proton might wait an extraordinarily long time before it finds itself on the other side of a barrier. How long exactly is the next uncomfortable number? There is a sequence. It begins with the simplest thing in the universe, a proton, which is to say a hydrogen nucleus, which is to say a single positive charge moving through the plasma of the solar core at speeds the temperature of 15 million Kelvin demands. Alone, it is nothing remarkable. The solar core contains something in the range of 10 to the power of 57 of them, which is a number so far outside ordinary intuition that it stops being a number and becomes a kind of placeholder for vastness. Each one moving, each one occasionally rarely meeting another. The first step happens when two of them meet closely enough, and tunnel through the Coulomb barrier closely enough that the strong nuclear force catches them. They bind. But binding two protons together into a stable nucleus requires something else to happen simultaneously. One of the protons must change. It must convert through the weak nuclear force from a proton into a neutron. And in doing so, it releases two things. A positron, which is an anti-electron, carrying a positive charge away from the site, and a neutrino, which carries energy and almost nothing else, and which will leave the sun entirely within a matter of seconds. What remains is a deuterium nucleus, one proton, one neutron bound together, the simplest possible form of heavy hydrogen. This step, just this first step, is the bottleneck of the entire process. The conversion of a proton to a neutron via the weak force is genuinely, stubbornly slow. Not slow in any human sense, slow in the sense that the probability of it occurring during any given close encounter between two protons is extraordinarily small. A proton in the solar core waits, on average, something like 3 billion years before this happens to it. We will come back to that number in the next chapter because it deserves its own space. For now, the step has happened. Deuterium exists. The deuterium nucleus does not wait long, within seconds, and the contrast with those 3 billion years is its own kind of violence, that the deuterium encounters another free proton. The strong force reaches out. The proton binds to the deuterium nucleus, and the result is helium-3, 2 protons, 1 neutron bound together. This reaction releases a gamma-ray photon, a packet of electromagnetic radiation carrying energy, born in the core, beginning immediately what will become a very long journey outward. So after 2 steps, we have helium-3, a positron, a neutrino, and a gamma-ray photon. The positron will almost immediately encounter a free electron, the plasma is full of them, and the two will annihilate each other, producing 2 more gamma-ray photons. The positron carries away its charge and a small amount of mass energy, and then it ceases to exist as matter. The neutrino has already left. The gamma rays remain, absorbed almost immediately by the surrounding plasma, contributing their energy to the thermal bath of the core. Now the third step. 2 helium-3 nuclei, produced by 2 separate runs through the first and second steps, approach each other and fuse. This collision produces helium-4, 2 protons, 2 neutrons, the standard helium nucleus, the stable end product, and it releases 2 free protons which return to the plasma and will eventually participate in the chain again. That's pp1, the dominant branch of the proton-proton chain responsible for somewhere between 83 and 85% of the Sun's energy output. Net result: 4 hydrogen nuclei have become 1 helium-4 nucleus, 2 positrons, 2 neutrinos, 2 gamma-ray photons, and the energy released by the positron annihilations. The chain is complete. The accounting closes, except, and this is the part that carries the whole video, the helium-4 nucleus weighs less than the 4 protons that went in, not much less. The difference is about 0.7% of the original mass, 0.7%. If you had 100 protons worth of mass at the start, you end with 99.3 protons worth of helium and 0.7 protons worth of something else. That something else is energy, not a byproduct of the process, not waste heat or a side effect. The mass itself converted. The 0.7% did not go somewhere else as matter. It ceased to be matter and became energy, in the precise ratio Einstein's equation specifies, the missing mass, multiplied by the speed of light squared. The number sounds small, 0.7%. You could be forgiven for thinking it inconsequential, but multiply it by the mass of hydrogen the Sun processes every second, roughly 600 million tons, and 0.7% of that is 4 million tons of mass converted to pure energy every second continuously, without pause, for 4.5 billion years and counting. Every photon that has ever illuminated this planet, every degree of warmth the atmosphere has ever held, every photosynthetic reaction that has ever occurred in every leaf that has ever grown, all of it came from that 0.7% deficit, from the small exact shortfall between the mass of 4 protons and the mass of 1 helium nucleus. The chain itself is almost austere in its structure. 3 steps, 2 inputs at the first step, 1 at the second, 2 helium-3 nuclei at the third, several particles produced and disposed of along the way. The net transaction is clean, hydrogen in, helium out, mass deficit converted to radiation. But clean does not mean simple, and the 3 steps conceal a patience at the first one that has no analogy in ordinary experience. The chain can proceed quickly once deuterium exists. The problem is making deuterium exist in the first place. The problem is step 1, and the weak force and the 3 billion year wait. That is the number the next chapter belongs to. 3 billion years. Not the age of the solar system, not the time since the first complex cells appeared on Earth. Just the average time a single proton spends in the solar core before the first step of the proton-proton chain happens to it. Before it meets another proton at precisely the right distance, tunnels the barrier, converts via the weak force, and becomes part of a deuterium nucleus. 3 billion years of moving through plasma, colliding with other particles constantly, and the core is not empty, is about as far from empty as matter gets, but not fusing, just moving and colliding and bouncing and continuing, 3 billion years before the specific, improbable, weak force-mediated event that starts the chain. The Sun is 4.6 billion years old, which means some of the protons currently in the solar core have been there longer than the average wait time, and simply haven't fused yet. Not because something went wrong, just because probability is not a schedule. I want to try to feel the shape of that number rather than just state it, though I'm not sure language is the right tool for it. 3 billion years ago on Earth, the most complex life forms in existence were single-celled organisms, bacteria and archaea, living in shallow seas, doing chemistry. There were no plants, no animals, no nervous systems of any kind. The continents were not in their current positions. Nothing that could be described as familiar existed anywhere on the surface of this planet. That is how far back 3 billion years reaches, and a proton in the solar core is doing nothing in particular for that entire duration. Just existing in plasma. Waiting, if you want to use that word, though the proton has no experience of it. Just present. Just moving. Just not yet fusing. This is the rate that determines everything. The sun is not a fast reactor, it is a slow one. Embarrassingly slow in some respects. A kilogram of solar material produces energy at a rate roughly 1,000,000 times lower than a kilogram of human metabolic tissue. Your body, gram for gram, runs hotter than the sun's core. Not in temperature, but the core is 15 million Kelvin, but in power output per unit mass. The sun is vast enough that its total output overwhelms any comparison, but the core itself is not a roaring furnace. It is more like a very large, very dense, very hot mass of material doing something extraordinarily slowly across an extraordinary volume. And this slowness is not a flaw. This is the sentence I keep returning to. The slowness is not a design compromise or an unfortunate limitation of the physics involved. The slowness is what makes the sun stable for long enough for any of this to matter. A star that burned through its hydrogen quickly, that ran the proton-proton chain at a faster rate, would exhaust its fuel in millions of years instead of billions. Life on Earth required billions. Not as a minimum, just barely cleared. Billions and billions. Enough time for single-celled organisms to slowly, haltingly, across countless dead ends and extinctions, produce something complex enough to eventually ask questions about the sun. That process could not have happened in a fast star. It needed a slow one. And the sun is slow because the first step of its fusion chain depends on the weak nuclear force, which is weak. Weak in the technical sense, meaning it operates at very short ranges and with very low probability per interaction. And because a weak force event requires a specific, rare, quantum mechanically mediated conversion that simply does not happen quickly. The patience is structural. It is written into the physics of the weak force. Nobody arranged it. It emerged from the values of the fundamental constants of nature. The coupling strength of the weak force, the mass of the proton, the energy scales involved. And if those constants were different, the rate would be different, and the sun would be different, and the duration available for biological complexity to develop on a planet orbiting it would be different. This is not an argument about fine-tuning or design. It is just a chain of consequences. The weak force has a particular strength. That strength sets the rate of deuterium production. That rate sets the sun's lifespan. That lifespan set the available window for what happened on this planet. The proton waits 3 billion years. In that waiting, in the accumulated improbability of that specific timescale, the sun's longevity is preserved. And in that longevity, the conditions for everything that eventually became curious about it were slowly, accidentally assembled. There is something in that sequence that I find difficult to move past quickly. Not because it implies anything particular about intention or purpose, just because the chain from weak force coupling strength to the existence of a species that can calculate that coupling strength is very long and mostly unplanned, and holds together more than it probably should. The proton doesn't know it's waiting. The sun doesn't know it's burning slowly. These are not acts of patience in any sense that involves a mind. But the outcome, the quiet, stubborn, 3 billion year reluctance at the first step of an otherwise fast chain, produced a star old enough to be circled by a planet complex enough to notice. That's not nothing, even if nobody arranged it. The photon doesn't travel outward. That's the first thing to understand, and it takes a moment to sit with because it contradicts something that feels obvious. Light travels in straight lines. Light moves at the speed of light. A photon born in the solar core, 700,000 kilometers from the surface, should, if you just apply the arithmetic naively, cross that distance in about 2.5 seconds. That's the calculation. Speed times distance. The number is real and the arithmetic is correct, and it describes something that does not happen. What actually happens is this. A gamma-ray photon is produced in the core during a fusion event, released as 2 nuclei bind and the mass deficit converts to energy. The photon exists. it begins to move at c, because that is the only speed it has access to, in some direction determined by the physics of the interaction that produced it. It travels, in the solar core, at 150 grams per cubic centimetre, the average distance it covers before it encounters another particle, and is absorbed is somewhere between a fraction of a millimetre and a few centimetres, depending on its energy and the local density. Then it is absorbed. The electron or nucleus that absorbs it holds that energy for an extraordinarily brief interval. We are talking about timescales far below any human perception, intervals that have no common language analogue, and then re-emits a photon. Not the same photon. A new one, with similar but not identical energy, travelling in a direction that has essentially no relationship to the direction the original photon was travelling. Random. The new direction is effectively random. And then that photon travels its few millimetres or centimetres and is absorbed again, and re-emitted again, in another random direction. This is the walk, not a journey, not a path. A sequence of random steps, each one very short, each one pointing somewhere unrelated to the last, through a medium so dense that straight-line progress is not available as a strategy. The photon is not finding its way to the surface. It has no way. It is just stepping and stepping and stepping in no particular direction through the dark interior of a star. The mathematics of this kind of motion has a name. The random walk, sometimes called the drunkard's walk, which is a name that has stuck because it captures something true about the geometry. Imagine someone leaving a lamppost, taking steps of fixed length but in completely random directions. After many steps, how far have they gotten from the lamppost? The answer on average is not the number of steps multiplied by the step length. It is the square root of that number multiplied by the step length. Progress, net displacement from the starting point, grows not linearly with the number of steps but with the square root of the number of steps, which are much, much slower. Apply this to the solar interior. The radius of the Sun is 700,000 kilometres. The mean free path of a photon, the average step length, in the deep interior is very roughly a centimetre or so, though it varies considerably with depth and density. To cover 700,000 kilometres in steps of 1 centimetre in a straight line would require 70 billion steps. In a random walk, to achieve the same net displacement requires not 70 billion steps, but 70 billion squared steps, which is a number, 5 times 10 to the 21st, that translates at the speed of light between steps to somewhere between 10,000 and 170,000 years. The range is wide because the solar interior is not uniform. Near the core, the density is highest and the steps are shortest and the walk is most tortured. Further out in the radiative zone, the density drops, the steps lengthen, the walk opens up somewhat. But the total time integrated across all zones comes out in that range. Tens of thousands of years minimum, 170,000 years in some estimates. Now here is the thing I find genuinely difficult to hold in mind, and I want to say it carefully because I think it's easy to pass over. The photon that eventually emerges from the solar surface is not the photon that was produced in the core, not in any meaningful sense. The photon born in a fusion event is a gamma ray, carrying around 1 million electron volts of energy. Each time it is absorbed and re-emitted, the new photon has slightly different energy, shifted by the thermal conditions of the plasma around it. Over hundreds of thousands of absorptions and re-emissions, the energy degrades. 1 million electron volts becomes 100,000, becomes 10,000, becomes 1,000, becomes... By the time that something finally escapes the photosphere at roughly 1 electron volt, visible light, the identity is lost in transit. The energy survives. What began as a gamma ray arrives as the warm light of a star, carrying no memory of what it was, having been absorbed and recreated so many times that the original photon exists only as a statistical ancestor of the thing that eventually left. It is a strange kind of continuity. The energy is preserved, that part holds. The conservation law does not break, but the carrier has been replaced thousands of times over by something that shared the energy and then passed it on. Like a message copied by hand so many times that the paper it was originally written on is dust, and the handwriting has changed, and the language has drifted, but the words, the actual content, are still there. Almost. The photon that emerges from the solar surface and crosses 150 million kilometers to reach your window does it in 8 minutes. 8 minutes, after a journey that took up to 170,000 years to bring it from the core to the surface. That contrast doesn't have a good analogy. I've tried a few and they all collapse under the weight of the actual numbers. The interior crossing is not long in the way a road trip is long, or in the way a century is long, or in the way the age of the dinosaurs is long. It is long in the way that geological time is long, the kind of duration in which continents move, species appear and vanish, ice ages come and go, and then 8 minutes. The gamma ray that leaves a fusion event in the solar core carries roughly 1 million electron volts of energy. That number needs a reference point. An electron volt is a very small unit. It is the energy gained by a single electron accelerating across a 1 volt potential difference, which is not a description that means much outside of physics. But comparisons help. The photons in visible light carry between roughly 1.7 and 3.1 electron volts. Radio waves carry fractions of 1,000th of an electron volt. X-rays used in medical imaging carry somewhere between 100 and 100,000. Gamma rays from nuclear reactions, the kind produced in the solar core, sit at 1 million or above. So the photon born in fusion is not just high energy in a relative sense. It is high energy in the sense of being in a completely different regime from the light that eventually leaves the sun's surface. The gap between 1 million electron volts and 1 electron volt is not a slope, it is more like a cliff face, traversed one handhold at a time, across an enormous stretch of time, through a process so gradual it has no single identifiable turning point. What happens step by step is this. The gamma-ray photon is absorbed by the surrounding plasma. An electron or an ion takes it in, and almost immediately re-emits a photon. The re-emitted photon has an energy determined not by what came in, but by the local conditions of the plasma. Temperature, density, the thermal state of the material at that particular depth in the sun, and those conditions set a ceiling on the photon's energy. The plasma can only emit photons as energetic as its temperature allows, and while the solar core is hot enough to produce gamma rays, the plasma doesn't re-emit cleanly at the same energy. The recoil of the absorbing particle, the thermal averaging across many interactions, the fact that one high-energy photon often produces multiple lower-energy ones in the emission process, all of this pushes the energy distribution downward. This happens again and again. Each absorption and re-emission event is a small step down the energy scale, not because energy is being lost, the total energy in the system is conserved, the thermal energy of the plasma absorbs and redistributes it, but because the form of the energy is changing. Individual photon energy is gradually, repeatedly, step by patient step, reduced. The high-energy single photon becomes several photons of moderate energy, which become many photons of lower energy, which become a vast number of photons of very low energy by the time the cascade reaches the outer layers. This is the translation I keep reaching for when I try to describe it. Not degradation exactly. That word implies loss, implies something going wrong. What is actually happening is more like a message being rendered into a different language. The information, the energy, is preserved. The medium changes. A single shout in the core becomes eventually a sustained murmur at the surface. The content is the same. The form is almost unrecognizable. By the time the photon energy works its way through the radiative zone, that enormous shell between the core and the convective zone, where energy moves primarily by this absorption and re-emission process, the characteristic photon energies have already dropped substantially from the gamma-ray range into X-ray territory, then into ultraviolet. The plasma temperature at each depth sets the distribution. The deeper you are, the hotter, the higher the characteristic energy. Rising through the radiative zone is rising through a temperature gradient that spans from 15 million Kelvin at the core to a few 100,000 at the base of the convective zone, and the photon population at each level reflects the temperature of the material around it. In the convective zone, the energy transport mechanism changes. Radiation gives way to convection, hot plasma physically rising, carrying energy upward, cooler plasma sinking. The photons in the convective zone still undergo absorption and re-emission, but the bulk motion of the plasma is now doing most of the carrying. The temperature continues to drop. The characteristic photon energies continue their long descent. At the photosphere, the visible surface, the layer thin enough for light to finally escape, the temperature is approximately 5,800 Kelvin. And at 5,800 Kelvin, the peak emission of a black body sits squarely in the visible light range. Between roughly 500 and 700 nanometers, 1 to 2 electron volts per photon. Green, yellow, orange. The colours your eye registers most easily on a clear afternoon. Now, the human eye. The eye did not evolve to detect light in general. It evolved to detect the specific light available to organisms living on the surface of this particular planet, orbiting this particular star. The peak sensitivity of the human eye, the wavelengths at which our photoreceptors respond most efficiently, sits between about 500 and 560 nanometers, green and yellow-green, which is very close, not coincidentally, to the peak emission wavelength of the Sun. This is not a design coincidence. It is an evolved one. Organisms whose photoreceptors happen to be most sensitive near the peak of solar emission could gather more information per unit of available light than organisms whose sensitivity lay elsewhere. Over hundreds of millions of years that advantage accumulated. The eye tuned itself, gradually, to the star. 1 million electron volts, filtered through hundreds of thousands of years of random walking and absorption and re-emission, and thermal averaging across 700,000 kilometers of plasma, emerges as roughly 1 electron volt and lands on a retina that evolved specifically to catch it. The gamma ray and the eye are connected by that entire chain, one at each end, neither aware of the other. The photosphere releases what the core spent so long producing, and 8 minutes later it arrives, already translated into exactly the language the eye was shaped to read. At some depth in the Sun, the plasma thins, not suddenly. There is no sharp boundary, no membrane, no line crossed. The photosphere is not a surface in the way a table has a surface. It is a zone, roughly 500 kilometers thick, across which the solar material transitions from opaque to transparent. From a state in which photons cannot travel more than a few millimeters before being absorbed, to a state in which they can travel freely, outward, into space. The transition happens because the density drops. Fewer particles per cubic centimeter means fewer opportunities for absorption. The mean free path, that average distance between interactions, lengthens from millimeters to kilometers to, eventually, something effectively infinite. The photon that was being passed from particle to particle, re-emitted in random directions, redirected constantly, suddenly finds itself with nothing in the way. It leaves. No particular moment marks this. The photon does not accelerate. It was already moving at c, and c is all it has. It does not change direction by choice. It simply continues in whatever direction it was last emitted, and this time nothing stops it. The plasma behind it thickens away into the Sun's interior. The space ahead of it opens, 150 million kilometers. That is the distance from the photosphere to Earth, approximately. It varies. Earth's orbit is an ellipse, but 150 million is the number that has settled into common use, and it is close enough. At the speed of light, 150 million kilometers takes 499 seconds, 8 minutes and 19 seconds. The photon that spent somewhere between 10,000 and 170,000 years moving through 700,000 kilometers of solar interior now crosses 150 million kilometers in the time it takes to boil water, or read a few pages, or have a short and slightly inconclusive conversation about something that doesn't matter much. I don't think there is anything to add to that contrast. I've tried a few times to find a way to frame it that adds something, and I keep arriving at the same conclusion. The numbers are already doing everything. Any analogy I reach for ends up being smaller than the thing it's supposed to represent. Any elaboration softens rather than sharpens. So just the numbers: 170,000 years, 700,000 kilometers, inside 8 minutes, 150 million kilometers. Outside, the interior crawl and the exterior crossing are not two phases of the same journey in any experiential sense. They belong to different categories of time. One unfolds across a duration in which human civilizations could have risen and fallen 100 times. The other fits inside a coffee break. The photon carries no record of the interior journey. It doesn't arrive tired, it doesn't arrive changed, it is not at this final stage, not in the 8 minutes. It moves through the vacuum of space at exactly the speed it moved through the last fraction of the photosphere, because nothing in the vacuum is slowing it, absorbing it, redirecting it. Vacuum is, for a photon, essentially frictionless. The journey from the Sun to Earth is the easy part, if easy means unimpeded. Space is mostly nothing. The solar wind thins rapidly with distance. The density of particles between the Sun and Earth is extraordinarily low, something like 5 to 10 protons per cubic centimetre near Earth, compared to 10 to the 57th in the solar core. The photon crosses this near emptiness in a straight line. It arrives. It hits something: atmosphere, a leaf, a window, a retina. And in that collision the 8-minute journey ends. The photon is absorbed. Its energy transfers to whatever it hit. It ceases to exist as a photon. No ceremony. That's not a complaint, just an observation. The journey that started in a fusion event in the solar core, that moved through 170,000 years of random walking, that degraded from a gamma ray to visible light across hundreds of thousands of absorption and re-emission events, ends the same way every step of the interior journey ended. With absorption. Something takes the energy in, and the Sun, at this exact moment, is producing more, has been producing more continuously, without pause, for 4.6 billion years, will produce more for approximately 5 billion years further, 8 minutes from Sun to Earth. The universe is not sentimental about arrivals. Every second, approximately 65 billion neutrinos from the Sun pass through every square centimetre of your body. Right now, through the back of your hand, through the table if there's one in front of you, through the floor, through however many meters of building and soil are below you, out the other side of the Earth, and onward into space. Not slowing, not deflecting, not leaving any trace of having passed through at all. This is not a poetic exaggeration. It is a measurement. The number has been calculated from the standard solar model and confirmed by experiment, and it is approximately correct for anyone on or near Earth's surface. 65 billion per square centimetre per second. You are being traversed continuously by particles produced in the core of the Sun 8 minutes ago, and you will never feel any of them. The neutrino's indifference to matter is the thing that makes it both extraordinary and extraordinarily difficult to work with. It interacts via only two forces: gravity, which is far too weak at this scale to matter, and the weak nuclear force. The weak force operates at ranges smaller than an atomic nucleus. For a neutrino to interact with anything, it has to pass within that range of a nucleus, which requires a proximity so close that even in dense matter it almost never happens. A neutrino can pass through a light year of solid lead, with only a 50-50 chance of interacting with anything. This is the property that makes neutrinos so useful as witnesses. The photons we see from the Sun are ancient, not 8 minutes old. The energy they carry is up to 170,000 years old, degraded and re-emitted so many times that it carries no direct information about the core conditions that produced the original gamma rays. What we see when we look at the Sun is the photosphere, the surface, the outermost visible layer. The core is entirely hidden behind 700,000 kilometers of opaque plasma. Neutrinos pass through that plasma as though it isn't there. A neutrino produced in a fusion event in the solar core escapes the Sun in approximately 2 seconds. 2 seconds to cross 700,000 kilometers of the densest material in the solar system, because the material is, for a neutrino, barely material at all. Then 8 minutes across 150 million kilometers of space. Then through Earth, through whatever is in the way, and gone. If you could catch one, it would be carrying direct information about a nuclear reaction that occurred in the solar core 8 minutes and 2 seconds ago, not 170,000 years ago. 8 minutes. The neutrino is the only real-time signal from the heart of the Sun. Ray Davis decided to catch some. Davis was an American chemist and physicist working at a Brookhaven National Laboratory. In the mid-1960s, he designed an experiment to detect solar neutrinos using a target of perchloroethylene, a common dry cleaning fluid chosen for its high chlorine content. Chlorine-37 can very rarely absorb a neutrino and convert to argon-37. The argon atoms, once produced, could be chemically extracted and counted. The rate of argon production would give the neutrino flux. The problem with detecting something that passes through a light year of lead with barely a scratch is that everything else gets in the way first. Cosmic rays, high-energy particles from space, would produce false signals in any surface detector, drowning out the neutrino signal entirely. So Davis went underground. The Homestake mine in Lead, South Dakota, 1,478 meters below the surface. A mile of rock above the detector, filtering out the cosmic rays while leaving the neutrino, which barely notice rocks, unimpeded. The detector itself was a tank, 380,000 litres of perchloroethylene, roughly 100,000 gallons of dry cleaning fluid, sitting in a cavern underground in the dark waiting. The experiment ran for years. Davis would periodically flush the argon atoms out of the tank, a few dozen atoms at a time, extracted from hundreds of thousands of litres of fluid, and count them. Each argon atom represented one neutrino interaction, one moment when a particle produced in the solar core 8 minutes before had, against all probability, briefly noticed the detector existed. The results when they came were wrong, or seemed wrong. Davis was detecting roughly 1/3 of the neutrinos the standard solar model predicted should be arriving. Not a small discrepancy, not a measurement error. Persistent, reproducible deficit of about 2/3. Either the solar model was wrong, or the experiment was wrong, or something was happening to the neutrinos between the Sun and the detector that nobody had accounted for. This became the solar neutrino problem, and it occupied physicists for 3 decades. The resolution when it came was not in the experiment and not in the solar model. It was in the neutrinos themselves. Neutrinos, it turned out, oscillate. They shift between different types or flavors as they travel. The neutrinos produced in the solar core are electron neutrinos, the type Davis's detector could catch, but by the time they reached the Homestake tank, a significant fraction had converted to muon, or tau neutrinos, which the chlorine detector could not detect. They were all arriving. Davis was only seeing the ones that hadn't changed in transit. The solar model was right. The experiment was right. The neutrinos were doing something nobody knew they could do. Confirming this took until 2001, with results from the Sudbury Neutrino Observatory in Canada which could detect all neutrino flavors. The total neutrino flux matched the solar model exactly. The deficit vanished when you counted everything. In 2002, Ray Davis received the Nobel Prize in Physics. He was 88 years old. He had spent more than 30 years being told, in various registers of politeness, that his numbers were probably wrong. They weren't. The neutrinos had been arriving all along, carrying 8-minute-old news from the solar core. Davis had been counting the ones he could see. The rest had simply changed into something his tank couldn't catch in transit without anyone knowing that was possible. The light you see from the Sun is old. The neutrinos passing through you right now are not. The eclipse of May the 29th, 1919, happened on a cloudy morning. At Principe, a small island off the west coast of Africa, Arthur Eddington and his colleague Edwin Cottingham had travelled several thousand miles and waited several weeks for 4 minutes of useful observation, and the sky that morning was overcast. A thunderstorm had moved through overnight. The clouds did not clear until approximately 30 minutes before totality, and even then they remained, thin in places, thicker in others, passing across the field of view in a way that could not be predicted or controlled. Eddington took 16 photographs through gaps in the cloud. Most were unusable, a handful were not. At Sobral, in northeastern Brazil, a second expedition led by Andrew Crommelin had better conditions and a larger telescope, but encountered its own difficulties. A focus problem with the primary instrument meant the best data came from a smaller backup telescope that nobody had expected to be the crucial one. This is the experiment that, when the results were announced in November 1919, made Einstein famous overnight. It is often described as a triumph. Looking at the conditions under which it was conducted, triumph seems like a word chosen after the fact. What the experiment was trying to do was simple in principle and very difficult in practice. General relativity predicted that light passing close to a massive object would have its path bent by the curvature of space-time the object produced. The Sun was the most massive nearby object, and a total solar eclipse was the only condition under which stars close to the Sun's limb, normally invisible in the solar glare, could be photographed. By comparing the apparent positions of those stars during the eclipse to their known positions when the Sun was elsewhere in the sky, any displacement caused by the Sun's gravitational influence could be measured. Einstein's prediction was a deflection of 1.75 arc-seconds for a star at the Sun's limb. An arc-second is 1/3600th of a degree. 1.75 of them is an angle so small it is essentially invisible to the naked eye. To measure it required comparing photographic plates taken months apart under different conditions, with different thermal states of the equipment, with stars in different positions, and extracting a shift of less than 0.002 of a degree from all that noise. There was also a competing prediction. Newtonian mechanics, treating light as a stream of particles with mass, also predicted that light would bend around the Sun. Newton's version produced a deflection of 0.87 arc-seconds, exactly half Einstein's value. The two predictions were different enough to distinguish if the measurement was precise enough, but close enough together that imprecision in the data could blur the boundary between them. The measurements from Sobral's main telescope, which turned out to be compromised by the focus problem, gave a figure close to the Newtonian value and were eventually set aside. The backup telescope at Sobral and Eddington's Principe plates, analysed together, gave a figure of approximately 1.75 arc-seconds, Einstein's number, not Newton's. The announcement was made at a joint meeting of the Royal Society and the Royal Astronomical Society on November 6, 1919. J.J. Thomson, who chaired the meeting, described it as one of the greatest achievements in human thought. The next morning Einstein was in the newspapers. I want to stay with the physics of what was actually found because the story of the expedition can easily crowd out the thing the expedition was measuring. The stars near the Sun's limb were not where they should have been. They were displaced, slightly precisely, by the amount Einstein's equation said they would be. Their light had passed close to the Sun on its way to Earth, and that passage had bent it. The paths the photons travelled were not straight lines. They were curves, following the geometry of space-time warped by the Sun's mass. Now, what does it mean for light to bend under gravity? In Newtonian mechanics, the bending of light can be calculated by treating photons as particles with mass, small mass but mass. Gravity acts on mass, so it acts on photons, so light bends. This is consistent and produces a number, 0.87 arc-seconds. It treats light as a material thing that gravity can grab. In general relativity, the bending is larger, 1.75 arc-seconds, because gravity is not a force acting on mass, but a curvature of space-time itself, and that curvature affects the geometry through which everything travels, including light. Massless light bends not because gravity pulls it, but because the space it moves through is curved. The path of least resistance, the straight line through curved space, is not a straight line in flat space terms, but the outcome is the same either way. Light responds to gravity, and something that responds to gravity participates in gravity. It is not exempt. It cannot pass through a gravitational field without being deflected, and deflection means the field is acting on it. And a field acting on something means that something has gravitational mass, in the only sense that he matters observationally. It behaves as though it does. The photon has no rest mass. We have been through that. But a photon passing a massive object does not travel straight. It curves. By an amount that can be calculated, predicted, and measured with photographic plates on a cloudy morning on a small island off the coast of Africa. The 1919 result was not the cleanest experiment ever done. The data had problems, the error bars were wide. Subsequent measurements, radio interferometry in the 1970s, the Hipparcos satellite in the 1990s, confirmed the deflection to much higher precision, matching Einstein's prediction to about 1 part in 1,000. But 1919 was the first time. The first time a photograph showed starlight arriving from the wrong place, bent by something it had passed on the way, moved by a force that was not supposed to apply to it. Light, it turned out, was not exempt from the accounting. The Jefferson Physical Laboratory at Harvard University is not a dramatic building. It is a brick building, the kind that universities accumulate without particular intention, built in the late 19th century and added to over the decades in the way that functional buildings are added to, pragmatically, without much concern for the overall shape. In 1959, it contained a vertical shaft, roughly 22.5 meters from basement to roof, not a purpose-built experimental space, just a tower. The kind of architectural feature that exists in old buildings because somebody needed a stairwell or a service shaft, or simply because the structure required it. Robert Pound and Glenn Rebka Jr. chose it because 22.5 meters was what they had. What they were trying to measure was gravitational redshift, the predicted shift in the frequency of light as it travels through a gravitational field. Einstein's general relativity, and in fact his earlier equivalence principle work from 1907, predicted that light climbing out of a gravitational well should lose energy. Its frequency should decrease, its wavelength should stretch. The shift should be proportional to the height climbed and the strength of the gravitational field. At Earth's surface, over the 22.5 meters, the predicted shift was approximately 2.5 times 10 to the power of negative 15. This is not a number that has an intuitive scale. It is a fractional change in frequency so small that it makes the word tiny seem inadequate. The frequency of a gamma ray is on the order of 10 to the 18 Hz. A shift of 10 to the negative 15 of that is a change of about 1 Hz. 1 cycle per second out of a billion. To measure that, you need a source and a detector that are both extraordinarily monochromatic, that emit and absorb at frequencies sharp enough that a shift of 1 part in a quadrillion is detectable rather than lost in the natural spread of the signal. In 1958, Rudolf Mossbauer discovered that certain atomic nuclei embedded in a crystal lattice can emit and absorb gamma rays without the usual recoil energy loss that blurs the signal. The crystal absorbs the recoil collectively, and the result is a gamma ray with a frequency precision far beyond what had previously been achievable. This is the Mossbauer effect, and without it the Pound-Rebka experiment could not have been done. The technology and the question arrived fortuitously within a year of each other. Pound and Rebka used iron-57, a radioactive isotope that emits gamma rays at 14.4 kiloelectron volts. They placed a source of this radiation in the basement of the Jefferson Tower and a detector at the top 22.5 meters above. Gamma rays emitted at the bottom would travel upward, climbing against Earth's gravity and arrive at the detector. If gravitational redshift was real, the arriving photons would have a slightly lower frequency than when they left. The problem was verification. How do you confirm that the arriving photons are redshifted, rather than simply concluding that your detector isn't responding at the right frequency? Pound and Rebka's solution was to move the source. By slowly oscillating the emitting material, moving it toward or away from the detector at a carefully controlled speed, they could use the Doppler effect to shift the emitted frequency by a known amount. When the Doppler shift exactly cancelled the gravitational redshift, the detector responded optimally. The speed required to achieve this cancellation gave them the magnitude of the gravitational shift. The speed required was about 0.7 millimeters per second, less than a millimeter per second, the drift of a very slow insect. That was the velocity needed to compensate for the gravitational redshift across 22.5 meters of Earth's gravitational field. The measured shift matched the prediction of general relativity to within about 10%, later refined to 1% by Pound and Snyder in 1964. The last of the 3 classical tests of general relativity had been confirmed. In a brick building in a repurposed tower, with a radioactive source on a platform that had to be moved at less than a millimeter per second to compensate for the effect of gravity on light. Now, what does this actually mean? A stone thrown upward loses kinetic energy as it climbs. This is familiar, completely unremarkable. Gravity pulls the stone back, work is done against that pull, and the kinetic energy converts to potential energy as the stone rises. The stone slows. At the top of its arc, if it has one, it has traded all its kinetic energy for potential energy and sits momentarily still. A photon cannot slow down. It has no kinetic energy in the classical sense. Its speed is fixed at c and cannot change. But it does have energy, entirely in its frequency, entirely in its quantum mechanical nature. And when it climbs through a gravitational field, that energy decreases. The frequency drops. The photon does not slow, it reddens. The mechanism is different from the stone. The outcome is functionally analogous. Both are losing something to gravity on the way up. The stone loses speed, the photon loses frequency. In both cases, the gravitational field has extracted a cost. This means a photon leaving the sun, climbing out of a gravitational well far deeper than anything on Earth's surface, arrives at Earth with less energy than it had when it left. The shift is measurable. The sun's surface gravity is about 28 times Earth's, and the photon climbs from there across 150 million kilometers of diminishing gravitational potential. The resulting redshift is small but real, and it has been confirmed independently through solar spectroscopy. Light climbing out of the sun loses energy to the sun's gravity. Not because the sun reaches out and takes something, because climbing costs something for everything that climbs. The photon is not an exception. The Harvard Tower proved it over 22.5 meters in a brick building in 1960, with a source moving at less than a millimeter per second, and a detector waiting at the top for photons that arrived, exactly and measurably slightly changed. The universe charges for altitude. Even light pays. The sail on Icaros was 14 meters across each side. 14 meters of polyamide film, 7.5 microns thick. A micron is a millionth of a meter. 7.5 of them. The film was thinner than a human hair, thinner than most things you have ever touched without noticing how thin they were. It was coated on portions of its surface with reflective material, and it was folded, very carefully, into a package small enough to fit inside a spacecraft launched on a rocket that had other things to do. In June 2010, the Japan Aerospace Exploration Agency deployed it in space. The package unfolded, the sail spread out to its full 14 by 14 meters, and the sun began pushing it, not metaphorically, not in the loose sense of sunlight warming a surface and creating some secondary effect. The photons streaming from the sun carried momentum, exactly as Maxwell's equations had implied in 1865, exactly as Lebedev had measured in 1899, and when those photons struck the Icaros sail, they transferred that momentum to it. Each photon individually contributed a force so small it has no everyday analogue. Collectively, across the full area of the sail, the force amounted to something like 1.12 million newtons, about 1/10 of a gram of weight equivalent. That is a very small force. It is also a continuous force. The sun does not stop pushing. There is no fuel to run out of, no engine that overheats, no propellant to exhaust. The photons keep arriving, the force keeps applying, and in space, where there is no air resistance, no friction, no drag of any kind, a continuous force, however small, produces continuous acceleration. The spacecraft gets faster, slowly, persistently, without stopping. Icaros demonstrated this. The mission confirmed that the spacecraft's trajectory was being measurably altered by solar radiation pressure, that the sail was not decorative, not experimental in the hope-it-works sense, but functional. The sun was steering the spacecraft. Light was doing what 3 centuries of physics had said it should be able to do, and it was doing it in a way that Japanese engineers could track with instruments and compare against predictions. LightSail 2, launched by the Planetary Society in 2019, went further. Its 32 square metre sail, deployed from a small CubeSat, a category of spacecraft roughly the size of a loaf of bread, was used to actively raise the spacecraft's orbital altitude. By rotating the sail to catch more or less radiation pressure at different points in its orbit, the mission demonstrated controlled manoeuvring using light alone, not drifting, steering, or... The spacecraft climbed higher in its orbit by adjusting its angle to the sun, using photon momentum the way a conventional thruster uses propellant. This is the part that sits with me when I think about the arc from Kepler to here. In 1619, Kepler watched comet tails point away from the sun and guessed that something emanating from the sun was pushing them. He had no mechanism. In 2019, an engineering team at the Planetary Society used that same push to adjust the orbit of a spacecraft smaller than a suitcase, using a sail thinner than a human hair, controlled by software tracked by ground stations. The mechanism is now so well understood that it is used for navigation. The force scales with distance, as any force from a point source should. Close to the sun, radiation pressure is higher, enough to be a nuisance for spacecraft designers who have to account for it whether they want to or not. The Messenger probe, which orbited Mercury, used its solar panels as impromptu sails to make fine trajectory corrections, adjusting their angle to the sun to change the radiation pressure they received, and thereby tweak the spacecraft's path more delicately than thrusters alone allowed. The engineers were not being clever. They were accounting for a force that was there whether they accounted for it or not. Farther out the force diminishes. At Earth's distance, the radiation pressure from the sun on a perfectly absorbing surface is about 9 micronewtons per square metre. At Mars, roughly half that. At Jupiter, about 1/30th. The light spreads as the inverse square of distance and the pressure with it. A solar sail is most effective close to the sun, which is why some proposed mission architectures involve unfurling the sail only after a close solar approach, catching the strongest push near perihelion and carrying that momentum outward. The physics of all of this is not new. Maxwell wrote it down. Lebedev measured it. What is new is the engineering patience to make the materials thin enough, the deployment mechanisms reliable enough, the guidance systems precise enough that something you can actually launch on a rocket will respond to it usefully. Photon momentum is real enough to be budgeted for, real enough that if you don't account for it, your spacecraft ends up in the wrong orbit. Real enough that 2 separate missions, separated by 9 years, used it to go somewhere specific. The sun is losing 4 million tons of itself per second as light. Some of that light is pushing spacecraft. Not many, not fast, but measurably, continuously, in exactly the direction the physics says it should. That is no longer a theory, it is a logistical consideration. In a PET scanner, the medical imaging device used in hospitals to detect tumours and map brain activity, a radioactive tracer is injected into the patient's bloodstream. The tracer emits positrons as it decays. Each positron travels a very short distance through tissue, slowing as it goes, and then meets an electron. The two particles annihilate. Two gamma-ray photons fly outward in opposite directions. Detectors surrounding the patient catch both photons, note the timing, triangulate the origin point, and build an image. This happens millions of times per scan. It happens in hospitals today. It is so routine that the engineering around it is mature enough to be reimbursed by insurance. I mention this first because annihilation is sometimes presented as an exotic phenomenon, something that happens in particle accelerators, in the early universe, in extreme conditions far from ordinary experience. It doesn't. It happens in medical centers. It happens in the upper atmosphere when cosmic rays produce particle showers. It happens in the solar core during the proton-proton chain, when the positrons released in deuterium formation meet the surrounding electrons almost immediately and vanish. Annihilation is not exotic. It is, in certain contexts, mundane. The exotic part is what it demonstrates. So, what actually happens? An electron and a positron are antiparticles of each other. Same mass, 9.109 times 10 to the negative 31st kilograms, or 0.511 mega electron volts expressed as energy via E equals mc squared. Opposite charge, the electron negative, the positron positive. In every other respect, identical. When they meet at low relative velocity, when neither is moving particularly fast relative to the other, they do not bounce. They do not scatter. They cease to exist. Both of them, completely. What replaces them is two photons, gamma rays, each carrying exactly 0.511 mega electron volts of energy travelling in precisely opposite directions. The 0.511 is not approximate. It is not rounded for convenience. It is the exact rest mass energy of one electron or one positron, since they are equal, calculated from E equals mc squared with no remainders, no losses, no inefficiency. One particle's worth of mass becomes one photon's worth of energy, twice over simultaneously. The two photons travel in opposite directions because momentum must be conserved. The electron and positron, approaching each other at low speed, have a combined momentum of approximately 0 in the centre of mass frame. After annihilation, the total momentum must still be approximately 0. Two photons of equal energy travelling in opposite directions satisfy this exactly. Their momenta cancel. The geometry is enforced by a conservation law that does not negotiate. Nothing is left over. Not a fragment of electron, not a residual positron, not a slightly degraded version of either particle limping away from the interaction. The matter is gone. The energy is in the photons. The transaction is complete and the accounting closes without remainder. This is why annihilation is the clearest demonstration of mass-energy equivalence available. Not the clearest theoretical demonstration, the clearest physical one, happening in real space with real particles, measurable with real detectors. Every other demonstration involves approximation somewhere, or inference, or a chain of reasoning between the observation and the conclusion. Nuclear binding energy differences require knowing the masses of nuclei to high precision and doing subtraction. The sun's mass loss requires measuring luminosity and applying a formula. The 1919 eclipse required comparing photographic plates taken months apart and extracting a small angular displacement from noise. Annihilation requires none of that. You put in two particles with known mass. You get out two photons with energies that exactly match those masses converted via E equals mc squared. You measure the photon energies, 0.511 mega electron volts each, confirmed to many decimal places across decades of experiments. And the equation either holds or it doesn't. It holds, every time, in every laboratory that has ever run the measurement, in every PET scanner that has ever produced an image, in the solar core right now, where the positrons from deuterium formation annihilate with core electrons in timescales so short they are effectively instantaneous relative to everything else in the proton-proton chain. The number is always 0.511. The directions are always opposite. Nothing is ever left over. What strikes me about this, and I want to be careful not to overstate it, is that annihilation doesn't demonstrate that mass can be converted to energy under special conditions. It demonstrates that mass and energy were the same thing all along, and that under certain conditions the form changes. The electron didn't transform its mass into energy the way a car transforms fuel into motion, with losses and heat and mechanical inefficiency. The electron's mass was its energy. The 0.511 mega electron volts was always there, expressed as rest mass, waiting for a condition meeting its antiparticle that would allow it to be expressed differently. The photons that emerge are not new energy. They are the same energy that was in the particles re-expressed. Changed form, not converted in the sense of a transaction between separate things, but revealed. The same quantity, previously wearing one set of units, now wearing another. The boundary between matter and energy in annihilation is not crossed. It turns out not to exist. The electron and positron were energy all along. The photons are energy. The difference between the before and the after is not the amount of energy in the system, that stays constant exactly, but the form it takes. Particles on one side, radiation on the other, same quantity, same conservation laws, same universe. In the solar core, the positrons from the proton-proton chain annihilate within microseconds of being produced, adding their 0.511 mega electron volts each to the thermal energy of the plasma, contributing to the warmth that works its way outward across 700,000 kilometers and 170,000 years and 8 minutes to arrive here. Two particles met. Both are gone. Two photons remain, carrying exactly what the particles were. That is not a model of what happened. That is what happened. The sun looks permanent. That is the first problem with thinking about this clearly. It rose this morning as it has every morning of every human life that has ever been lived, and it will set tonight, and it will rise again tomorrow, and nothing about its appearance suggests that anything is happening to it. It is simply there, a fixture, the most reliable object in human experience, the one thing that has never failed to appear, never varied enough in its daily presentation to cause alarm, never given any indication from its surface that something fundamental is occurring inside it. But the sun is not permanent. It is a slow subtraction, and the arithmetic of that subtraction, laid out carefully, produces a picture that is genuinely different from the permanent fixture the morning sky implies. Start with the number from the beginning of this video. Every second, the sun converts approximately 4.3 million metric tons of its mass directly into energy via the proton-proton chain. Not burning, not evaporating, not shedding mass in the way a candle sheds wax, converting. The mass ceases to exist as mass and becomes radiation, in the precise exchange rate Einstein's equation specifies. 4.3 million tons per second. Per minute, that is roughly 258 million tons. Per hour, about 15.5 billion tons. Per day, approximately 371 billion tons. Per year, somewhere around 135 trillion tons. These numbers grow quickly and then become hard to hold, so let me stay with the per second figure and instead change the timescale. The sun is 4.6 billion years old. A billion seconds is approximately 31.7 years. A billion years is therefore approximately 31.7 billion seconds. Call it 3.17 times 10 to the 16th seconds. 4.6 billion years is roughly 1.45 times 10 to the 17th seconds. At 4.3 million tons per second, across 4.6 billion years, the sun has converted approximately 6.2 times 10 to the 23rd metric tons of its mass to radiation. That is a very large number. But the sun's total mass is approximately 1.989 times 10 to the 30th kilograms. Call it roughly 2 times 10 to the 27th metric tons. The fraction of the sun's total mass that has been radiated away over its entire 4.6 billion year lifetime is therefore something in the region of 0.03%. The Sun has lost less than 0.1% of its mass since it formed. I find this number quietly disorienting, and I want to sit with it for a moment because it works in both directions. On one hand, 4.5 billion years of continuous mass conversion and the Sun has barely changed in mass. It is still, to within a fraction of a percent, the same gravitational presence it has always been, holding the solar system in the same configuration, the planets in approximately the same orbits. On the other hand, that tiny fraction, that less than 0.1%, is the sum total of every joule of sunlight that has ever fallen on this solar system, every degree of warmth this planet has ever experienced, every photosynthetic reaction that has ever occurred, every storm, every ocean current, every glacial advance and retreat, all of it powered by something that amounts to less than 0.1% of the Sun's total substance. The efficiency is, in a plain arithmetic sense, extraordinary. Not because the conversion rate is high, as 0.7% of hydrogen mass per fusion cycle is actually quite low by some measures, but because the reservoir is so vast that even a slow, reluctant proton-by-proton process running for billions of years produces only a small dent in it. Now, forward. The Sun's approximately halfway through its main sequence lifetime. The core, the region where fusion occurs, roughly the innermost 10% of the Sun's mass, contains a finite supply of hydrogen. That supply is being depleted at the rate the proton-proton chain permits, which is slow, which is why the Sun has lasted this long, which is why we are here to do this accounting. Current stellar models estimate that the core hydrogen will be exhausted in approximately 5 billion years, give or take. The uncertainty in that figure is not small. Stellar evolution models involve a number of parameters that carry real uncertainties, but the order of magnitude is well established, 5 billion years, roughly the time that has already elapsed since the Sun formed. When the core hydrogen is gone, the physics of the Sun changes. The fusion that has been producing outward pressure against gravitational collapse stops in the core. The core contracts. The outer layers, responding to the changed pressure balance, expand. The Sun becomes what astronomers call a red giant, a much larger, somewhat cooler, more luminous object that will eventually extend to roughly the current orbit of Earth. Mercury will certainly be consumed, Venus almost certainly. Earth's fate depends on details of the mass loss during the red giant phase that are genuinely uncertain. That is 5 billion years away. The number matters less than the shape of it. The Sun is not permanent. It is a quantity of hydrogen being slowly converted to helium, and helium accumulating as ash in the core, and the fraction of hydrogen remaining decreasing every second at a rate of 4.3 million tons per second, continuous, patient, arithmetically exact. Right now, tonight, while this is playing and you are wherever you are, the Sun is on the other side of the planet and the Earth is between you and it, and the Sun is nonetheless radiating in all directions, and some of that radiation is reaching the night side of the atmosphere, and the Sun is, at this exact moment, slightly less massive than it was when this sentence started. By a small amount, a very small amount, but exactly, always exactly. Come back to the room, the same room you were in at the beginning of this, or a different one. It doesn't matter. The physics applies regardless of where you are. There is a window somewhere near you, or there was one earlier today, and at some point light came through it. Maybe it landed on your arm, or the floor, or the surface of a table, or your face. You probably didn't think much about it. Light comes through windows, that's what windows are for. But that light was hydrogen, not made from hydrogen, not powered by hydrogen in the way a fire is powered by wood, with the wood remaining as ash on the other side of the reaction. The light itself, the photon that crossed 150 million kilometers of space in 8 minutes and passed through the glass and landed somewhere on you, was, before it was a photon, a small piece of the Sun's mass, a fragment of proton, or the energy released when a proton converted to a neutron in a deuterium nucleus, or the momentum released in an annihilation event when a positron met an electron, and both ceased to exist as matter. That specific history is impossible to trace for any individual photon. But the chain is real. The mass that left the sun as radiation became the light that arrived here. 4 million tons per second, leaving as photons, each one carrying what was once substance. The warmth you felt on your skin this morning was some number of steps back in a long and specific process, part of a star. This is not a metaphor. That is the point I keep wanting to make, and the point this entire video has been building toward. It is not that the light is like something that used to be mass, or that the energy is equivalent to what the mass was, in the way that $1 is equivalent to 100 cents. A conversion between two different things that happen to be the same value. The light is what the mass is. The same quantity, same conservation law, same universe, same accounting, no transaction between categories because there is only one category. We spent a very long time thinking there were two. Matter on one side, energy on the other. You had one or you had the other, and converting between them was a special event, a dramatic occurrence, something that required nuclear conditions or extreme physics. Einstein's 1905 paper unsettled that division. The proton-proton chain makes it daily, continuously in the core of the nearest star. Pair annihilation makes it completely, two particles of matter becoming two photons of radiation with nothing in between. No conversion moment, just matter in one instant and light in the next. The distinction was always in the description, not in the thing being described. Think about the photon sitting in your room right now, the one that came from the sun this morning and was absorbed by the wall or the floor or you. It started as a gamma ray in the solar core carrying a million electron volts. It spent up to 170,000 years being absorbed and re-emitted, softening step by patient step, from gamma to X-ray to ultraviolet to visible. It crossed 150 million kilometers in 8 minutes. It arrived here carrying roughly 1 electron volt and landed on whatever it landed on and gave that energy to whatever absorbed it. At no point in that journey was it not mass. At no point was it not energy. It were both, always, because those are not two things. The sun is lighter than it was 8 minutes ago, by the amount of mass that left as the light currently between us and it. That mass is in transit. It has not been destroyed. It has not been lost. It is out there in the form of photons crossing space, some of it about to arrive on Earth, some of it heading toward other stars, some of it that will travel for billions of years before encountering anything at all. The mass is real. It is just wearing different clothes. I started this video with a paradox. Something that weighs nothing is draining the sun of 4 million tons every second. The contradiction was between the zero rest mass photon and the measurable mass loss of the star producing it. Massless light carrying away real mass. That contradiction dissolves. I don't think it resolves exactly, it dissolves. Once you accept that rest mass and total energy are not the same quantity, and that the sun's mass loss is the transfer of energy momentum into photons, and that energy momentum is what mass is. The photon has no rest mass because it cannot rest. The sun loses mass because mass and energy are the same physical quantity and the energy is leaving. The paradox was in the words, in the categories we built and then forgot we had built, in the assumption that massless meant inconsequential and that mass was a thing matter had while energy was a thing matter produced. Neither of those is quite right. Mass is a form of energy that happens to be still. Energy is a form of mass that happens to be moving. The proton-proton chain is the process that shifts a small fraction of the first kind into the second, and the second kind crosses space at sea and arrives at whatever is in the way and becomes heat or chemistry or a signal in a retinal cell, and the universe's accounting remains balanced throughout. The light through your window tomorrow morning will have left the sun 8 minutes before it arrives. The mass it carries left with it. The star will be by that exact amount smaller, and somewhere in the solar core, a proton that has been waiting for 3 billion years will finally fuse, and the chain will continue, and the sun will keep spending itself into light, patient and exact and continuous, for approximately 5 billion more years. The room is quiet now. That's the end of the physics. If this video gave you something, a thought worth keeping a night that ended a little differently, the best way to support this channel is on Patreon. We're working toward 200 members, which is the number that keeps the Sleepy Physicist going without question. If you can, it matters more than I usually say. The link is in the description. And if not, you being here was already enough. Thank you.